Okay, so today's video we're going to be looking at the exact values of circular functions, and this is really important. I cannot stress this enough. If you don't know your exact values, everything else will fall apart after this. These are things that you need to learn, but I want to talk about some different ways in which you can generate them, because I want you to be careful about thinking that you can just rote learn a list of numbers. That might be fine over the next 2 or 3 weeks while we're focused only on this topic, but by the time the exam comes around, by the time it crops up as part of another topic down the track or whatever it might be, you won't have ready access to them. The other thing I think that's risky with just rote learning is when you're there in the exam and you're trying to recall a fact, you have no way of knowing that what you have remembered is correct. So what I want you to focus on instead is a way that you can generate the numbers you need through mathematical fact and therefore be certain of what you have found, as opposed to just trying to rote learn them and recall them in a test. Okay. So what we want to look at here is being able to calculate the value of sine, cosine and tan for a number of different angles without needing our calculator. Now obviously if you've got your calculator and I ask you, tell me what the value of sine of 45 degrees is, you can put it in your calculator and your calculator will tell you what it is. But in a tech-free assessment, you need to be able to know what sine of 45 degrees is. Okay, and there are ways to do that, and we want to look at that today. We're also going to bring in some of our symmetries from the last lesson, and obviously familiarity with our unit circle. Okay, so the first thing I want to start with is actually exact values we've already talked about. So we want to think about our exact values for 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Well, and I guess 360 technically, which is the same as 0. We want to start to really just work in radians. So let's think about those instead as being 0 degrees is still 0 radians. 90 degrees, that's half of 180, so it's half of pi on 2. 180 degrees we know is pi radians. And 270 degrees is 1.5 lots of 180, so 3 on 2 times pi, 3 pi on 2. Okay, so if we think about the reason that we already know these values is because these are fixed points in our unit circle. So in our unit circle, 0 degrees is over here, or 0 radians, sorry, working radians. So I don't need the symbol because default is radians. 90 degrees, or pi on 2 radians, sorry, let's try for a straight line. Pi on 2 radians is up here. That's pi on 2. Pi is out here. And 3 pi on 2 is down here. Now obviously when I write the number here, I'm not indicating that this point is 3 pi on 2, I'm talking about that whole angle all the way around there is 3 pi on 2. But things get messy if I try to draw all 3 angles and label them separately. Okay, so I'm just labeling it at the line. Okay, so then we already know what the coordinates of these points are. So this point here, we know that's the point 1, 0. So therefore we know sine and cos at 0. We also know that this is the point 0, 1. This is the point -1, 0. And this is the point 0, -1. I also want us to remember, I haven't drawn in the tangent here, but what I want us to recall, you remember a couple of videos, we talked about the fact that using similar triangles in our circle enables us to say that tan is equal to sine divided by cos. So once we work out the sine and the cos value, we can divide the sine value by the cos value to get the tan value. Okay, so let's work our way around the circle. So let's think about at an angle of 0. So sine of 0 means the y coordinate at an angle of 0. So we can see that is 0. Cos of 0 is the x coordinate at an angle of 0. We can see that that is 1. Tan of 0, now actually we don't need to use sine divided by cos yet. We will a bit further down the track potentially. But it should also fit together. But tan of 0, we can see actually that the y value there is 0. So the y value on the tangent is 0. Equally, sine, which is 0, divided by cos, which is 1, 0 divided by 1 is 0 for the tan value. Okay, sine of pi on 2. So the y coordinate at an angle of pi on 2, that's 1. Cos of pi on 2, the x coordinate at an angle of pi on 2, that's 0. And tan of pi on 2, remember when the angle is pi on 2, the line never intersects with the tangent, and so therefore actually tan of pi on 2 is undefined. And we would also see that if we thought about dividing the sine value by the cos value. Sine of 1 divided by 0 can't divide by 0. That's undefined. Let's try writing that correctly. Undefined. Okay, sine of pi, so round here at 180 degrees, the coordinates of the point are negative 1, 0, so sine is the y coordinate, that is 0. Cos is the x coordinate, that is negative 1. And at pi, if we extend the line out to meet with the tangent, we can see that tan is 0. Again, doing the division, sine value divided by the cos value, 0 divided by negative 1 is 0. Then at 3 pi on 2, the coordinates are 0 and negative 1, and the y coordinate, therefore, sine of 3 pi on 2 is the y coordinate, that's negative 1, cos is 0, and tan is undefined again because we are parallel to the tangent. Okay, so any multiple of pi on 2, you should be able to calculate the exact value. It's only going to be 0, 1, or negative 1, or undefined, for sine, cos, or tan anywhere in the unit circle. If we looked at, sine of 12 pi, if you think about what's happening here, 1 pi, 2 pi, 3 pi, 4 pi, even multiples of pi are over here, and odd multiples of pi are over here. So you know that, sine of 12 pi is 0. Cos of 12 pi is 1. It's in this position over in the on the right hand side. Okay, they're the easy ones. Multiples of pi on 2, we should absolutely be able to calculate our exact values for. Then I want to think about exact values for 3 other important angles. 30 degrees, 60 degrees, and 45 degrees. In radians, 30 degrees is 1/6 of 180, so that's pi on 6. 60 degrees is 1/3 of 180, so that is pi on 3. And 45 degrees is 1/4 of 180, so that's pi on 4. Okay, so what I want to introduce here is 2 what we call special triangles. And these 2 triangles enable us to generate the values of sine, cos, and tan for pi on 3, pi on 4, and pi on 6. So by remembering 2 triangles, we can generate the 9 different exact values that we need. This is the method that I use to find my exact values, okay? If you told me right now, snap your fingers, Miss Kelly, and tell me what sine of pi on 5 is, sorry, not pi on 5, sine of pi on 3 is, I know it's between one of 2 things, but I would draw the triangle to confirm it, okay? If you ask me about sine of pi on 4, I do know that one, because it's a bit different. But it's important, as I said, that you have a way to generate them. Okay, so the reason we can find exact values for 30 degrees, 60 degrees, and 45 degrees is actually because we can easily generate these triangles. So, the first triangle I want to think about, where we'll be able to deal with both 30 degrees and 60 degrees at the same time, is an equilateral triangle of side length 2. And what we're going to do is we're going to cut it in half so that we create a right-angled triangle. Okay, so we already know we've now made a right angle here. We know the equilateral triangle has a side length of 2, so this length here is 2. And we know we've cut it in half by dividing it in a right angle triangle, so we now know that this length here is 1. If we use Pythagoras' theorem, we can work out what this length is. And again, this is not a step I need to do every time. I know what that value is, but I can always generate it if for some reason it slips from my mind. So we know that Pythagoras' theorem tells us h squared plus 1 squared is 2 squared, so that is h squared plus 1 equals 4, h squared equals 3, and so h is the square root of 3. We don't need plus minus because it's a length we're talking about in this instance. Okay, so this value over here, this value over here is, is root 3. Okay, if we think about the angles of this triangle, we know that all the angles in an equilateral triangle are 60 degrees. So we know that this angle down here is 60 degrees, or pi on 3 radians. And we know that this angle up here is half of 60 degrees because we cut it in half when we divided the equilateral triangle. So half of 60 degrees is 30 degrees, or pi on 6. So what we have here is a right-angled triangle. Actually, I'm just going to write that pi on 6 in a different colour for a particular reason. And I might also write this one down here. Oh, sorry. Okay, so let's go with these two angles. Okay, so what I want us to think of, let's think about pi on 6 first. Okay, so we're simply going to use our right-angled trig, SOHCAHTOA. Okay, so if we're interested in pi on 6, which we are for now while I fill in the three values I've just encircled in green. If we're interested in pi on 6, that makes this length the opposite length, it makes this length the hypotenuse, and it makes, sorry, gosh, it's the end of the long day. It makes this length the adjacent, and it makes this length the hypotenuse. So, if we want to calculate sine of pi on 6, it would be the opposite length to pi on 6, which is 1, divided by the hypotenuse, which is 2. Okay, so sine of pi on 6 will be 1/2. Cosine of pi on 6 is the adjacent side, √3, divided by the hypotenuse, which is 2. And tan of pi on 6 is the opposite side, which is 1, over the adjacent side, which is √3. Now let's think about sine. Let's think about pi on 3. Sine, cos, and tan of pi on 3. So now, if we're interested in pi on 3, the blue angle, this length over here becomes the opposite, this length becomes the adjacent, and this is still the hypotenuse. So using our right-angled trig, sine of pi on 3 is opposite over hypotenuse, which in this case is √3 on 2. Cos of pi on 6 is adjacent over hypotenuse, which in this case is 1 on 2. And tan of pi on, sorry, I think I said pi on 6 earlier. I meant pi on 3, sorry. And tan of pi on 3 is opposite over adjacent, which is √3 over 1, so just √3. You can confirm any of those values using your CAS. If I were to type in, sine of pi on 6, it is indeed 1/2. If I were to type in, tan of pi on 3, it certainly is √3. Interestingly, I just want to show you tan of pi on 6, because there's obviously two different ways we could write that answer. Tan of pi on 6. The CAS tells us it's √3 on 3. Using my triangles, I tend to give that value as 1 on √3. It's perfectly correct to give it as 1 on √3. You do not need to rationalise denominators in maths methods, but if we were to rationalise this denominator by multiplying the numerator and denominator by √3, we would get √3 on 3. So they're the same thing. Either of those is perfectly fine. So very quickly, when I'm needing my exact values, what I will very quickly do is sketch my half an equilateral triangle. That's 1, that's 2. I know that that's √3. I'm interested in pi on 6, that's that angle up here, and then straight away I can work out what sine of pi on 6 is, 1/2, cos of pi on 6, √3 on 2, tan of pi on 6, 1 on √3. I can also get all the pi on 3 values from that one little triangle, a rough sketch on the side of my page during a SAC or a test or an exam. Okay. All right, let's think about pi on 4. So pi on 4 we can also generate from a triangle. So if we think about creating a right-angled isosceles triangle, okay? So right-angled, there's a right angle here. Isosceles means that these two lengths are 1, and the equal sides are of length 1. So these two lengths are equal, and it tells us that they are length 1 in this particular triangle. You can actually make them length anything and it'll work out the same, but you'll end up with fractions that you have to simplify when you do your ratios. So you want to stick with the smallest values. It's the same in the equilateral triangle. You could use an equilateral triangle of side length 1 or 17 or whatever it might be, and it just means that all of your side lengths will be scaled up, and when you do the fractions, when you do the divisions to find opposite over hypotenuse or whatever, you'll have fractions that cancel down to give you 1/2 no matter what numbers you choose. So start with the smallest numbers. So we're going to start with, in this case, in the second special triangle, 1, 1, 1 and 1. Again, by Pythagoras' theorem, we can calculate this hypotenuse length. Okay. So we know that x squared is equal to 1 squared plus 1 squared. So x squared equals 1 plus 1, which is 2, and therefore x is √2. And again, I don't need to do Pythagoras every time. I remember this triangle, it's 1, 1 and √2, and then from there I can calculate my exact values. Now the reason this is good for 45 degrees is because if it's an isosceles triangle, we know that these two angles, sorry, let's get a pen that's a bit wider. Let's try that one. These two angles are the same. They're equal, and we know they have to add up to 90 degrees because the sum of the angles in the triangle has to be 180. So therefore they have to be 45 each if they're the same and they add to 90. 45 is pi on 4. Okay. Now obviously we've got two angles of pi on 4 here, so we could call this side the opposite and this the adjacent, or the other way around, but given that they're both 1, it doesn't matter. Okay. And this is the hypotenuse, obviously. So now I can calculate my values of sine and cos and tan using my right-angled trig from the triangle. So sine of pi on 4 is the opposite side over the hypotenuse, so that is 1 on root 2. Cos of pi on 4 is the adjacent side over the hypotenuse, which is also 1 on root 2. And tan of pi on 4, opposite over adjacent, is 1. Again, let's just have a quick look. If I were to calculate, for example, cos of pi on 4 with my CAS will give me root 2 on 2. And again, that's just the same value as this, but with a rational denominator. So multiplying top and bottom by root 2. So either of those is perfectly fine. I give those values as 1 on root 2. There's no problem with that. But recognizing that those are the same thing is important. So you've got your two special triangles, okay? You've got your half an equilateral triangle, 1, 2, and root 3. That gives you pi on 3 and pi on 6. And you've got your isosceles triangle, 1, 1, and root 2, which gives you pi on 4. And from those two triangles, you can calculate all 9 values, depending on what it is that you need in your question. So my advice is draw the triangles, generate your values when you need them. If you rely on a table while you're doing your homework, for example, you won't have a table when you need it in a test. If you think you're going to learn the table, fine, but you see there's a lot of repetition, for particularly these ones, you know, which one's a half and which one's root 3 and 2, and have I remembered them the right way around? So I would strongly advise using the triangles. Okay, they're summarized here in a table, but as I said, I want you to really refrain from doing all this work with the table sitting next to you. I want you to practice needing to generate them, okay? And in doing that, you'll start to learn them a bit better. So for example, I actually don't ever need to draw this triangle because sine and cos are both 1 on root 2 and tan is 1, and I know those values. This one's the one I draw, just so I make sure I get my halves and root 3 on 2 around the right way, okay? What I will say is there are some patterns in this table that can help you to generate it, but yeah, so it's worth, you know, I'll show you that, but again, I personally rely on the triangles. So if you look at the sine column, I've got the angles listed in increasing order. That's important. And in the sine column, the first one, you can generate a pattern that all of them are root something over 2. Okay, root something over 2, root something over 2, root something over 2, root something over 2. Oh, sorry, not root 2 over 2, root something over 2. Okay, and then just count up. Root 0 over 2, which is obviously 0. Root 1 over 2, which is 1 over 2. Root 2 over 2, which is the same as 1 on root 2. Root 3 over 2, can't be simplified. Root 4 over 2 is 2 on 2, which is 1. And then you just reverse that for the cos. So again, they're all something on root 2. Again, you could not give your answer as root 4 on 2. That's not a simplified answer, but just as a way to generate them. So these are exactly the same, but in reverse. Root 0 on 2, which is 0. Root 1 on 2, which is 1. Root 2 on 2, which is the same as 1 on root 2. Root 3 on 2, and root 4 on 2, which is 2 on 2. And then from those, to generate the tan values, you really need to do your sine divided by cos to give you tan. Okay? So 0 divided by 1 is 0. Half divided by root 3 on 2 is half times 2 on root 3. And so your 2's cancel out and you get 1 on root 3. Okay. And you can generate them in that way. But again, use the triangles. Honestly, it's very easy. Try and practice it, see how you go. Okay, now we want to combine together our exact values with our symmetries. Okay, so once we know about the values of sine, cos, and tan for pi on 6, pi on 3, and pi on 4, we then know the values of sine, cos, and tan for any multiple of those values. Okay, so here, for example, cos of 2 pi on 3. So we want to think about where that is in the unit circle, and this is where you're going to need to start to practice with your fraction work and your radians. Okay, so cos of 2 pi on 3. So I might just draw myself a bit of a circle so I get a sense of what's happening here. So I want to think about where is 2 pi on 3 in the unit circle. What I want to think about is it's certainly going to connect to pi on 3, and it's actually, two lots of pi on 3. Now, obviously, if you think about dividing your circle into thirds, or into pi on 3, I should say, because it actually divides the whole circle into 6, that would be 1 pi on 3, which is 60 degrees, 2 pi on 3, 3 pi on 3, 4 pi on 3, 5 pi on 3, 6 pi on 3, okay, which is 2 pi. Okay, so 2 pi on 3 is actually pi minus pi on 3. That's it around here. Okay, that's where 2 pi on 3 is, all the way around there. And so we want to think about how does that connect to cos of pi on 3. Okay, so we know cos of pi on 3 is the x-coordinate at this green point. We want to know what the x-coordinate is at the purple point. Now, I haven't drawn a very symmetrical circle there, but clearly the x-coordinates will have the same value, but the purple value is going to be negative. The other way you can start to think about it is 2 pi on 3 is in the second quadrant. I know that cos is negative in the second quadrant. I either know it because I remember my acronym, or I know it because I know that cos is about x-coordinates, and in the second quadrant, x-coordinates are negative. This is definitely equal to a negative value, and it's going to be the negative of cos of pi on 3. And then we need to know what cos of pi on 3 is. So, quick rough sketch, that's pi on 3 down there, 2, 1, root 3, cos of pi on 3 adjacent over hypotenuse, so that will be 1/2. Okay, so this will be equal to negative 1/2. Cos of 2 pi on 3 will be negative 1/2. Okay, sine of 3 pi on 4, where is that in my unit circle? So I'm just going to draw a slightly bigger one. Where is that in my unit circle? 3/4 of pi, it's going to be there. 1/4 of pi, 2/4 of pi, 3/4 of pi, 4/4 of pi. Okay. You can think about it as pi minus pi on 4 if you want to. Okay, so that tells you it's in the second quadrant again. Sine is positive in the second quadrant, so this will be positive. So what we know is that sine at 3 pi on 4, which is the y-coordinate of this purple dot, is going to be the same as sine of pi on 4, which is the y-coordinate of the green dot. So it's going to be the same as sine of pi on 4. And then my exact values. Now I know that all the sine and cos of pi on 4 are both 1 on root 2. I remember those ones myself, but I can draw my little isosceles triangle, 1, 1 and root 2. That's pi on 4 there. So sine of pi on 4 opposite over hypotenuse, 1 and root 2. Okay, tan of 7 pi on 6. Sorry. Tan of 7 pi on 6. Okay, so it's going to be connected to pi on 6. We just want to work out where in the unit circle it is, which quadrant, so we know whether it's going to be positive or negative. So 7 pi on 6. So I want you to try and think about what's the nearest whole multiple of pi. So 6 pi on 6 is pi. Okay, so that's here. 7 pi on 6, therefore, is just going to be pi on 6 further on from there. So it's going to be around here in the third quadrant. So that would be 6 pi on 6 around there, and then plus another pi on 6 to get around to here. So that means it's going to relate to pi on 6 in the first quadrant. Now, we're interested in tan, and we actually know that these two things are going to have exactly the same tan value. They're both going to have the tan value that is the y-coordinate of that green point I've just drawn there. So tan of 7 pi on 6 is actually going to be exactly the same as tan of pi on 6. Again, you can use your sort of cast idea, you know. I know that 7 pi on 6 is going to be connected to pi on 6. I know 7 pi on 6 is in a quadrant where tan is positive, so it will be equal to positive tan of pi on 6. Now, again, my exact values. Pi on 6 is this angle up here, okay? A sixth of 180, it's a smaller one, smaller than a third of 180. This is 2, 1 and root 3. Tan of pi on 6 is opposite over adjacent, so that is going to be 1 on root 3. Okay. Sine of 13 pi on 6. So again, we're connected to pi on 6. We want to think about where are we in our unit circle. And again, I'm trying to think about what's a whole multiple of pi that's near there. So I know 12 pi on 6 is 2 pi. So that's around there. I know that's 12 pi on 6. And so therefore 13 pi on 6 is just going to be another pi on 6 past here. Okay, so we're going to have gone the whole way around and then a little bit more. So we're in the first quadrant, and in fact, obviously it's actually literally in the same position as pi on 6. So sine of 13 pi on 6 is going to be exactly the same as sine of pi on 6. They're in the same position in the unit circle, and therefore they have exactly the same y coordinate. Sine of pi on 6, I've got my triangle over here. I've already got pi on 6 highlighted. Sine is opposite over hypotenuse, so 1 on 2. Tan of negative 4 pi on 3. Okay, so this time we're going to go the other way around the circle. We're going to be dealing in thirds of pi. Okay, so again, you can sort of count 1 pi on 3, 2 pi on 3, 3 pi on 3, 4 pi on 3. Remember, we're going back around this way. Okay, or again, you can think about what's the nearest whole multiple of pi that's near there. So I know negative 3 pi on 3 will be around here at negative pi. Okay, that's that. And then obviously I just need to go 1 more pi on 3 past there to get to negative 4 pi on 3. So we'll be there. In the second quadrant, we're dealing with tan, okay? And so obviously we're going to have a negative tan value. It will be the negative of tan of pi on 3. Again, I've got my triangle drawn just up here in the previous question. So pi on 3, though, is the green angle I've just highlighted. Tan of pi on 3, opposite over adjacent. So root 3 on 1, so that's root 3. So therefore this is equal to negative root 3. And finally, cos of 15 pi on 4. Okay, so again, let's think about where we are in our unit circle. So I'm thinking 15 pi on 4 is sort of near 16 pi on 4. And 16 pi on 4 would be 4 pi. 16 pi on 4 is 4 pi. So that's going to be around here. That's 2 full laps. 2 pi, 4 pi. 2 full laps of the circle. And so that's 16 pi on 4. So 15 pi on 4 is just going to be pi on 4 before then. So pi on 4 before then is going to be just back here. So we'll be in the fourth quadrant where we know that cos is positive. We either know that from our cast rule, we know that because we know that cos is the x-coordinate, the x-coordinates are positive in the fourth quadrant. And so we know that this is going to have the same cos value as cos of pi on 4. Okay? So the x-coordinate of the green point is cos of pi on 4, the x-coordinate of the purple point is cos of 15 pi on 4, and they're clearly going to be the same thing. Okay? So this is equal to cos of pi on 4. Now again, I personally don't need my triangle for cos of pi on 4 because I know that sine and cos of pi on 4, here's the triangle up here I drew in a previous question, sine and cos of pi on 4 are 1 on root 2. And they're ones that I do remember. But again, having a way to generate them if you're not sure, okay, if I at some point I'm not sure, I know this is 1 root 2, this is my right angle here, both the angles are pi on 4, so you can use either of them. Cos adjacent over hypotenuse is 1 on root 2. Okay, so we want to play around with remembering the exact value. So again, I want you to not just sit there with a table next to you. There's no point in that. Anyone can refer to a table. If you have a table with you, it means you've got notes. It means you've got your CAS. You don't need a table. Okay, you will need these in a test or an exam where you don't have your notes and therefore you don't have your CAS and you can't just refer to something. So really try to practice being able to generate them in the heat of the question at the moment that you need them. And you then need to combine that together with your symmetries and your unit circle in finding cos of other multiples of pi on 3, pi on 6 and pi on 4. So the work today is from exercise 14F.